Welcome back, everyone. We're diving into the world of small language models today. You know, those AI programs that can understand and generate human language. We've had a ton of requests to break down how these smaller models are getting surprisingly powerful, especially compared to those massive ones we hear about all the time.
Yeah, it's a really exciting area. There's this big push to make powerful AI more accessible. And smaller models, well, they need less computing power, so they can run on everyday devices, like your phone even. Imagine AI built right into the apps you use every day. No need for a giant supercomputer miles away.
That would be incredible. No more waiting for responses, everything happening right on our devices. The research paper guiding our deep dive today is actually called Small LM2. When small goes big, data-centric training of a small language model, it's like a David and Goliath story for AI.
Totally. And just like that story, Small M2's secret weapon is all about using its resources wisely. See, with these smaller models, everything comes down to data quality. They just don't have the capacity to learn from huge amounts of data like the big guys, so every single piece of information has to really count.
So it's not just about how much data they have, it's about feeding them the right kind of data.
Exactly. It's kind of like, trading for a marathon. You wouldn't fuel yourself with just junk food, right? You'd plan out your diet carefully to get the best performance. Small language models need that same kind of high-quality data diet to achieve great results.
That makes a lot of sense. The paper mentions this multi-stage training idea. What is that exactly?
So think of it as a recipe with many different steps. Instead of throwing everything in at once, multi-stage training means feeding the model specific types of data in stages, like adding spices at just the right moment while you're cooking. This way, you can gradually shape the AI's abilities and focus on certain skills at each step.
Like building up to something more complex over time. So the researchers who created Small M2 started by looking at tons of existing data sets, right? Web text, code, even math, trying to find the best ingredients for their AI recipe.
Exactly. And two massive datasets for web text really stood out. One is called FindWeb Edu, which is focused on educational content. And then there's DCLM, which is more diverse and conversational. One's more about knowledge and reasoning, while the other is all about common sense.
Sounds like they each have their own strengths. So did the researchers have to choose one over the other?
That's where it gets really interesting. They found that a blend was actually the best approach. Small M2 was trained on a mix of 60% FindWeb Edu and 40% DCLM for its web text training. It's the best of both worlds.
A balanced diet for a well-rounded AI education. But what about something like math? That seems like it would be a real challenge for language models. Math needs that step-by-step reasoning, not just pattern recognition.
You're right, math is definitely tricky, but they came up with a really cool solution.
Okay, I'm intrigued. How did they teach small M2 to do math?
They actually created their own dataset called FindMath. And get this, they used another larger language model to help filter and select only the highest quality math problems with clear step-by-step explanations. It's like using one AI to train another.
Wow, that's crazy. So did this approach actually work? Did it help with the math?
The results were amazing. FindMath helped small M2 get a twofold improvement on this standard math reasoning benchmark compared to using other datasets. It really shows how powerful it can be to focus on curating the right kind of data.
That's incredible. So they figured out web text and math. What about coding? Did they use a similar approach there?
Absolutely. They created a dataset called Stackadoo based on this existing one called StarCoder 2 data. But instead of just using all of it, they used an AI filter again to pick out the most educational and well-documented code examples.
Interesting. So this AI filtering technique was used in multiple areas. That's pretty smart. But before we get into the details of these data sets and training stages, let's take a step back. Why should all of this matter to us? What's the bigger picture here? Why are we so interested in making these smaller language models so good?
Well, think about it. Smaller models running on everyday devices means you could have really powerful AI assistants right on your phone. They could understand you better and help you with your daily tasks.
Okay, I see where you're going with this. So we're talking about personalized education tailored to your learning style, healthcare applications, and who knows what else, all happening right in our pockets.
Exactly. And this is just the beginning. Now let's dive back into those training stages. How did they use all these data sets to make Small LM2 so capable?
Lead the way. What was the first stage all about?
So the first stage was all about building that strong foundation. They focused mainly on web text, using that 60-40 mix of FindWeb Edu and DCLM we talked about, plus a dataset called StarCoder Data for some general coding skills.
Kind of setting the stage for the more specialized training later on. What did they learn from this initial stage?
Well, they saw the model developing strong knowledge and reading skills, but its performance in coding and math were still lagging behind a bit. This confirmed that they needed those specialized datasets later on to really round out Small M2's skill set.
So a solid foundation, but still room to grow. What about stage two? What happened there?
Stage 2 was about addressing those gaps. They started introducing the Open Web Math Dataset, or OWM for short, at a low percentage, while also increasing the proportion of code data. It's like a gentle intro to math, but lots of practice on the coding side.
Makes sense. Did this approach work?
It did. They saw a significant improvement in coding performance across most programming languages, which shows that starting to prioritize code data early on was the right call. The OWM edition, though, didn't have a huge impact on math performance just yet. It needed more time to learn.
Okay, so coding is coming along nicely, but math still needs some work. Anything else interesting happened during stage 2?
There was this really interesting observation. So there's this benchmark called MMLU that tests a model's understanding across many different tasks. Small M2 achieved above random accuracy on a multiple choice version of it.
Above random. That doesn't sound too great.
It might not sound impressive at first, but it actually challenges some assumptions about small language models. Some researchers thought that smaller models couldn't handle multiple choice questions, but small M2 proved them wrong. It shows that even with limited capacity, long training durations can really help a model learn.
It's the slow and steady wins the race approach.
Exactly. And this discovery led them to tweak their recipe. They adjusted the ratio of FineWeb Edu to DCLM, aiming to get those multiple choice results even better.
I'm noticing a pattern here. Constant tweaking and experimentation. All right, stage 3. What new challenges and successes came up?
Okay, so stage 3 was all about adding even more specialized data and refining the model's abilities. They increased the math data by adding in the text portion of Infim Web Math, bringing the total math contribution to around 10%.
So now they're getting serious about math. What about coding? Did they stick with the same data set?
Nope, they made a big change there. They replaced star-coded data with that curated StackEdu dataset we talked about earlier, plus they added some Jupyter notebooks from StarCoder 2, which are kind of like interactive code examples with lots of context.
So they really loaded up on the high-quality code data this time. Did everything go smoothly?
Well, they hit a little snag. There was a noticeable spike in their loss metrics during stage 3.
Loss metrics. For those of us who aren't AI experts, can you explain what that means?
Think of it as a temporary setback, like hitting a plateau during training. It's not always clear why these spikes happen, but they can indicate the model is having trouble learning from the data.
A bit of a mystery glitch then. Did they manage to fix it?
Luckily, most of their evaluation metrics were covered by the end of stage 3, so it seems like the model was back on track.
Phew, good to hear. Okay, on to the grand finale. What happened in stage 4?
Stage 4 was what they call the decay phase, where they gradually reduced the learning rate. Think of it like slowly turning down the heat on the stovetop to let all the flavors blend. It's a common technique to make those final adjustments and prevent what's called overfitting.
Okay, overfitting. What exactly does that mean?
Imagine memorizing all the answers for a test instead of actually understanding the material. Overfitting is kind of like that. The model gets too good at performing on the training data, but struggles to generalize to new information.
So the decay phase is like making sure the model isn't just a one-trick pony. What data did they use in this final stage?
They introduced their highest quality math datasets, FineMath 4 Plus and Inphi WebMath 3 Plus, plus a small percentage of a dataset called AugGSM8K, which is an augmented version of that GSM8K math benchmark.
They really went all in on the math this time. What about the other areas like web text and code?
They expanded StackEdu to include even more programming languages, kept that English web data flowing, and also added in Cosmopedia v2 to make sure small MM2 had lots of different types of text to learn from.
Cosmopedia, that sounds familiar. Can you remind us what that one is?
Oh, it's a data set of these high-quality synthetic textbooks, blog posts, and stories. Kind of like giving the model all sorts of reading material to learn and expand its knowledge.
A little bit of everything to round it all out. So after 4 stages, countless data points, and a lot of fine-tuning, how did small M2 actually perform?
The results were impressive. Improvements across all the benchmark tasks they were tracking. But the biggest gains were in coding and math, showing that their data-centric approach and those specialized data sets really made a difference.
That's fantastic. But they didn't stop there, right? Didn't they do something to enhance the model even further?
You're right, they took it a step further and extended small M2's context length. This is really important for a language model's overall capability.
Context length. Remind me what that is again?
Think of it as the model's short-term memory. It's all about how much text it can process at once. They trained small M2 to handle much longer chunks of text, up to 8,000 tokens.
So going from reading tweets to reading entire chapters of a book, that's quite a leap.
Exactly. It opens up so many more possibilities for what small M2 can handle.
A memory upgrade without sacrificing any smarts. It sounds like they really achieved something incredible, but how did it actually stack up against other models, the other small language models? Was it able to compete with the best of them?
That is the big question, and one we will answer after a quick break. Stay tuned.
Okay, so we're back, and I'm really curious to see how small M2 stacks up against the competition. Time for the ultimate test. How did this small but mighty language model perform against other models its own size?
Well, they put small M2 through a bunch of benchmark tests, comparing it to 2 other state-of-the-art small language models, QA-2.5-1.5b, and Llama 3.2-1b. The idea was to see how well it would do in all these different areas, from knowledge and reasoning to code generation and, of course, math problem solving.
So a real head-to-head competition. What were some of the key findings? What stood out from these evaluations?
Small M2 consistently outperformed both of its rivals in tasks involving knowledge and reasoning. Basically, this means it's really good at understanding information, retrieving it, and making logical connections between different pieces of knowledge.
So it's not just memorizing facts, it's actually using them to problem solve and answer questions. That's impressive.
Exactly. And here's something else interesting. It also did really well on tests it had never seen before, stuff that wasn't part of its training data.
I mean, it can generalize, right? Like take what it's learned and apply it to new situations. Isn't that a sign of true intelligence?
That's exactly what it is. It means it's not just regurgitating information. It can actually learn and adapt. Pretty impressive for a smaller model. Now, in terms of those specialized areas we talked about, like math and coding, small M2 still performed very well, even surpassing Llama-3.2-1b in both of those areas.
That's really promising, especially considering its size. Earlier, we talked about how they extended small M2's context length. Did that have a negative impact on its performance at all? I imagine handling all that extra information could slow things down or make it less accurate.
You'd think so, right? But that's what's remarkable. There was almost no drop in performance, even after extending the context length. In fact, small M2 really shined in those tests, specifically designed for long context scenarios. It can handle a lot of information without getting bogged down.
So they gave it a memory upgrade without sacrificing any of its smarts. It sounds like small M2 really is something special.
It really highlights the power of focusing on data quality. By being super careful about the data they use for training, they were able to create a small language model that performs way better than you'd expect for its size.
And they didn't stop there, did they? Didn't they also create even smaller versions of small M2?
Yes, they developed versions with 135 million and 360 million parameters. And guess what? These smaller versions also achieved state-of-the-art results for their respective sizes. This really shows that this data-centric approach can work across different scales.
That's incredible. So they created not one, but three high-performing small language models. But they didn't just keep all this amazing work a secret, right?
Oh, absolutely not. They released all the data sets they created, along with the code for small M2, to the entire research community. This is huge for the field because it allows other researchers to build upon their work and explore new possibilities.
That's what's so great about open science, right? Sharing knowledge and resources can really speed up progress. It's inspiring to see this level of collaboration in the AI field.
Definitely. It's paving the way for others to build on these advancements and hopefully create even more impressive small language models.
Speaking of the future, let's talk about the potential applications for these powerful, compact language models. What are some areas where small M2 and its smaller versions could make a real difference?
Well, the possibilities are vast. Imagine having truly intelligent AI assistants that could run right on your phone. They could give you personalized recommendations, help you manage your schedule, even translate languages in real time.
That would be a game changer for travel and communication.
And think about the impact on education. We could have personalized learning experiences that cater to each student's unique needs and learning styles.
That would totally revolutionize the way we learn. What about fields like healthcare or scientific research? Could these models have an impact there?
Absolutely. In healthcare, they could help with things like early diagnosis, personalized treatment plans, and even drug discovery. The possibilities are endless.
It sounds like these smaller language models could make a huge difference in areas that really matter. It's exciting to think about the benefits for society as a whole.
And that brings it to a thought-provoking question. What other potential applications can you imagine for these powerful, compact language models?
It's a question worth exploring. I have a feeling we're just scratching the surface of what's possible with this technology. I'm sure we'll see some truly groundbreaking applications emerge in the years to come. Thanks for joining us on this deep dive into the world of small but mighty language models. Until next time, keep exploring. It's incredible to think about the potential impact these smaller models could have, especially as they become even more powerful and easier to access. But before we get too lost in those possibilities, I'm curious about some of the challenges they faced. Were there any areas where small M2 struggled or maybe didn't quite meet expectations?
You know, that's a really good question. Small M2 did show impressive performance overall, but of course there's always room for improvement. For instance, even though it was great at math reasoning compared to other small models, it still falls short of those larger language models when it comes to things like accuracy and handling really complex math problems.
So there's still a gap between the small models and the giants, at least when it comes to those highly specialized tasks. Anything else? Any other limitations they ran into?
Well, another challenge is the cost of training. Even for a smaller model, it takes a lot of computing power and energy, which can be expensive and, it has environmental impacts too.
Right, training the model is like a marathon for computers. It takes a lot to get them to the finish line.
Exactly. Figuring out how to make that training process more efficient and sustainable is a really important area of research.
Sounds like some exciting challenges lie ahead. What are some of the things researchers are focusing on to overcome these limitations and make small language models even better?
Well, one really promising area is developing new training techniques that need less data and less computing power. Researchers are also looking into ways to make these models more adaptable so they can pick up new tasks and even new languages more easily without having to start the training from scratch every time.
So it's not just about size and efficiency, it's about making them smarter and more versatile learners. Fascinating.
And of course, there's always the ongoing challenge of improving their ability to reason and really grasp the nuances of human language. Models like Small M2 have come a long way, but there's still a lot of work to do before they can truly understand the complexity of how we communicate.
It sounds like there's a ton of exciting research happening in this field. What are some of the key takeaways you'd like our listeners to remember from our deep dive today?
I really hope they come away understanding that the future of AI isn't just about building bigger and more complex models. It's about making AI accessible to everyone, and smaller, more efficient models like Small M2 could be the key to that.
That's a powerful thought. Democratizing access to AI could lead to some incredible breakthroughs, solutions that could benefit everyone.
Absolutely. And I also hope our listeners understand just how crucial data quality is for training these models. It's not just about how much data you have, it's about carefully choosing the right kind of data to help them learn and grow.
Like we said earlier, giving them that balanced, nutritious data diet to reach their full potential.
Precisely. And finally, I hope everyone leaves this deep dive feeling optimistic and excited about what the future holds for AI. There are challenges, sure, but the progress we're seeing in small language models is really remarkable. I can't wait to see what amazing applications emerge in the years to come.
It's definitely a fascinating time to be following AI. Thanks for joining us on this deep dive into Small LM2 and the world of small but mighty language models. We hope you learned a lot and are just as excited about the future of AI as we are. Until next time, keep exploring. CACCA.